Can you name the four pillars that form the foundation of effective data organization and analysis? If you're drawing a blank, you're not alone. Many data scientists overlook these crucial concepts, leading to inefficient workflows and missed insights. In this video, we're going to unveil these four pillars: taxonomy, ontology, knowledge graphs, and semantics. Understanding these concepts can be the difference between drowning in data and surfing the waves of insights. Are you ready to transform your approach to data science? In the world of data science, effective organization is crucial for making sense of the vast amounts of information we collect. But have you ever wondered what the foundational elements of this organization are? Let's explore four interconnected concepts that form the pillars of data organization: taxonomy, ontology, knowledge graphs, and semantics. Together, these pillars create what we call the TOKS Framework in data science. It's a common misconception that these terms are interchangeable, but each plays a distinct role in structuring and understanding data. Taxonomy, derived from the Greek words taxes, arrangement, and nomos, law or science, has its roots in biological classification systems. Ontology, originating from philosophy, deals with the nature of being and existence. Knowledge graphs, a more recent development, emerged from computer science and artificial intelligence research. Semantics, with its origins in linguistics, focuses on the meaning and interpretation of data. Each of these pillars addresses specific challenges in data organization. Taxonomy provides a hierarchical structure for categorizing information, making it easier to navigate and retrieve data. Ontology goes beyond simple categorization, defining relationships and properties between entities. Knowledge graphs represent these relationships visually, allowing for complex queries and insights. Semantics ensures that the meaning of data is preserved and understood across different contexts and systems. The synergy between these concepts in modern data science is remarkable. Taxonomies provide the backbone for organizing data, while ontologies add depth and context. Knowledge graphs bring these relationships to life, allowing for dynamic exploration and discovery. Semantics tie it all together, ensuring that the data's meaning is accurately captured and interpreted. Neglecting any of these pillars can lead to significant data management issues. Without a proper taxonomy, data becomes disorganized and difficult to find. Lack of ontological structure limits our understanding of how different pieces of information relate to each other. Without knowledge graphs, we miss out on powerful visualization and querying capabilities. And without proper semantic understanding, we risk misinterpreting data or failing to extract its full value. Understanding these pillars can transform the efficiency of data analysis. By implementing a well-structured taxonomy, data scientists can quickly locate relevant information. A robust ontology allows for more nuanced and context-aware analysis. Knowledge graphs enable the discovery of hidden patterns and relationships, and a focus on semantics ensures that insights derived from the data are accurate and meaningful. As we delve deeper into each pillar, we'll see how they work together to create a comprehensive framework for data organization and analysis. Taxonomy provides the initial structure, organizing data into logical categories. This categorization forms the basis for more complex relationships defined by ontologies. These relationships are then visualized and made queryable through knowledge graphs. Finally, semantics ensure that the meaning and context of the data are preserved throughout the entire process. The historical development of these concepts reflects the evolving needs of data management. Taxonomies have been used for centuries to classify and organize information, from biological species to library cataloging systems. Ontologies gained prominence in the late 20th century as computer scientists sought ways to represent knowledge in artificial intelligence systems. Knowledge graphs emerged in the 2010s as a powerful tool for representing and querying complex relationships in large datasets. Semantics, while always important in linguistics, has become crucial in data science as we grapple with the challenge of making machines understand human language and context. In practice, these pillars often work in tandem. For example, a data scientist working on a recommendation system for an e-commerce platform might start by creating a taxonomy of product categories. They would then develop an ontology that defines relationships between products, such as complementary to or substitute for. This ontology could be represented as a knowledge graph, allowing for complex queries like find all products that complement item X and are frequently bought together with item Y. Throughout this process, semantic analysis ensures that product descriptions and user reviews are accurately interpreted and incorporated into the recommendation algorithm. The TOKS Framework also plays a crucial role in data integration and interoperability. As organizations deal with increasingly diverse and complex data sets, these pillars provide a common language and structure for combining and making sense of disparate information sources. A well-defined taxonomy and ontology can help map data from different systems to a common format. Knowledge graphs can represent the relationships between these disparate datasets, while semantic analysis ensures that the meaning of the data is preserved across different contexts. As we shift our focus to taxonomy, consider this. In a world drowning in data, could the key to efficient information management be as simple as creating the right categories? Let's explore how this fundamental concept forms the bedrock of effective data organization. Imagine walking into a massive library with millions of books, but no system to organize them. Finding a specific book would be like searching for a needle in a haystack. This is where taxonomy comes to the rescue. In the realm of data science, taxonomy serves as the backbone of classification, providing a structured approach to categorizing and organizing vast amounts of information. To understand taxonomy in action, let's consider a real-world example, the classification of living organisms. Biologists use a hierarchical system that starts with broad categories like kingdom and phylum, narrowing down to more specific levels such as class, order, family, genus, and species. This structure allows scientists to quickly identify and understand the relationships between different organisms. In data science, taxonomies follow a similar hierarchical structure. At the top, we have broad categories that encompass large groups of data. As we move down the hierarchy, these categories become more specific, allowing for precise classification of individual data points. This structure is crucial for creating a common language within an organization, ensuring that everyone understands and uses the same terminology when referring to specific types of data. However, developing effective taxonomies for complex datasets is not without its challenges. One of the primary difficulties lies in striking a balance between breadth and depth. A taxonomy that is too broad may not provide enough granularity for detailed analysis, while one that is too deep can become unwieldy and difficult to navigate. Data scientists must carefully consider the nature of their data and the specific needs of their organization when designing a taxonomy. Another challenge is maintaining flexibility in the face of evolving data landscapes. As new types of data emerge or existing categories shift, taxonomies must be adaptable enough to accommodate these changes without requiring a complete overhaul of the system. Despite these challenges, well-implemented taxonomies offer significant benefits, particularly in improving data retrieval and analysis speed. By providing a clear structure for data organization, taxonomies allow users to quickly narrow down their search to relevant categories, dramatically reducing the time spent sifting through irrelevant information. To illustrate this point, let's walk through the process of creating a basic taxonomy for a dataset. Imagine we're working with a large collection of customer data for an e-commerce company. We might start by creating top-level categories such as demographics, purchase history, and customer support interactions. under demographics. We could have subcategories like age, location, and occupation. Purchase history might include product categories, frequency, and average order value. This hierarchical structure allows data scientists and analysts to quickly locate specific types of information without having to search through the entire dataset. While taxonomies are powerful tools for data organization, it's important to recognize their limitations. One key drawback is their inability to represent complex relationships between different data points. For instance, in our e-commerce example, a taxonomy might struggle to capture the nuanced connections between a customer's purchase history, their demographic information, and their interactions with customer support. This limitation, however, doesn't diminish the value of taxonomies. Instead, it sets the stage for more advanced data structures. Taxonomies lay the groundwork for these sophisticated systems by providing a solid foundation of categorization and hierarchy. They serve as a crucial first step in the journey towards more comprehensive data organization and analysis. The true power of well-designed taxonomies becomes evident when we look at their impact on data search efficiency. Studies have shown that implementing a thoughtful taxonomy can reduce data search time by up to 50%. This dramatic improvement in efficiency not only saves time, but also enhances the overall quality of data analysis by ensuring that data scientists can quickly access the most relevant information for their projects. While taxonomies provide a solid foundation for organizing data, they only scratch the surface of the complex relationships that exist within information systems. Ontologies take data structuring to the next level, creating a rich tapestry of interconnected concepts and properties. This advanced approach to data organization can potentially boost data interoperability by up to 70%, revolutionizing how we understand and utilize information. Ontologies build upon the hierarchical structure of taxonomies by adding layers of complexity and meaning. They don't just categorize data, they define the relationships and properties between different entities within a domain. This allows for a more nuanced and comprehensive representation of knowledge, enabling systems to understand not just what things are, but how they relate to one another. At the core of ontologies are three key components: classes, instances, and properties. Classes represent general concepts or categories similar to the nodes in a taxonomy. Instances are specific examples or individuals within those classes. Properties are the attributes or relationships that connect classes and instances. For example, in a music ontology, artist could be a class, the Beatles an instance of that class, and recorded a property linking the artist to their albums. This structure allows ontologies to create a shared understanding of domain knowledge. By explicitly defining the relationships and properties within a field, ontologies ensure that all users and systems have a common language for discussing and working with data. This shared understanding is crucial in fields like healthcare, where precise definitions and relationships between medical terms can literally be a matter of life and death. The power of ontologies becomes evident when we consider how they enable more sophisticated queries and data integration. Unlike simple keyword searches, ontology-based systems can understand context and relationships. This allows for complex queries that can traverse multiple relationships to find relevant information. For instance, in a scientific research ontology, a query could easily find all experiments that use a specific technique were conducted by researchers from a particular institution and resulted in findings related to a specific gene. Creating an ontology often starts with expanding an existing taxonomy. Let's consider how we might transform a simple taxonomy of musical instruments into a basic ontology. In the taxonomy, we might have categories like string instruments, wind instruments, and percussion instruments, with specific instruments listed under each. To create an ontology, we would add properties and relationships. For example, we could add properties like material, wood, metal, etc., playing technique, bowed, plucked, blown, etc., and pitch range, high, medium, low. We could also define relationships like is played in to connect instruments to musical genres or requires to link instruments to specific skills or accessories. While ontologies offer powerful capabilities, they also present challenges, particularly in maintenance and updating. As knowledge in a domain evolves, ontologies must be updated to reflect new understanding. This can be a complex process, especially in large interconnected ontologies where changes in one area can have ripple effects throughout the system. Maintaining consistency and avoiding conflicts in these updates requires careful management and often specialized tools. Ontologies play a crucial role in semantic web technologies, forming the backbone of efforts to make web content more machine-readable and interoperable. By providing a structured way to represent knowledge, ontologies enable different systems to understand and communicate with each other more effectively. This is essential for the vision of a more intelligent, interconnected web, where software agents can perform complex tasks by understanding and combining information from various sources. The impact of ontologies on data interoperability is significant. By providing a common framework for understanding and relating different pieces of information, ontologies can dramatically improve the ability of different systems to share and integrate data. Studies have shown that implementing well-designed ontologies can improve data interoperability by up to 70%. This means faster, more accurate data sharing between different departments, organizations, or even entire industries. Consider a real-world example in the field of agriculture. An ontology-based system could integrate data from weather stations, soil sensors, satellite imagery, and crop yield records. This would allow farmers and agricultural scientists to make more informed decisions about planting times, irrigation schedules, and pest control measures. The ontology would define relationships between concepts like soil type, crop varieties, weather patterns, and pest outbreaks, enabling sophisticated analyses that could significantly improve crop yields and sustainability. As we move from theory to application, a new question arises. How can we transform the complex relationships defined by ontologies into a format that computers can easily process and humans can intuitively understand? Enter knowledge graphs, a powerful tool that's quietly reshaping how we interact with data. Knowledge graphs serve as a practical implementation of ontologies, bringing abstract concepts to life in a tangible, interconnected web of information. At their core, knowledge graphs consist of three fundamental elements: nodes, edges, and properties. Nodes represent entities or concepts, such as people, places, or objects. Edges, also known as relationships, connect these nodes, illustrating how different entities interact or relate to one another. Properties, on the other hand, provide additional context by describing attributes of both nodes and edges. This structure allows knowledge graphs to represent real-world entities and their relationships in a way that's both machine-readable and human-interpretable. For instance, in a knowledge graph about movies, you might have nodes representing films, actors, directors, and genres. Edges would connect these nodes, showing which actors starred in which films, who directed them, and what genres they belong to. Properties could include release dates for movies, birth dates for actors, or box office earnings for films. One of the most prominent applications of knowledge graphs is in powering recommendation systems. These systems analyze the connections between different entities to suggest relevant content or products to users. For example, a streaming service might use a knowledge graph to recommend movies based on not just what you've watched before, but also the directors, actors, and genres you seem to prefer. By leveraging the rich interconnections within the knowledge graph, these recommendations can be surprisingly accurate and diverse. Major tech companies have embraced knowledge graphs to enhance their services. Google's Knowledge Graph, introduced in 2012, powers many of the informative panels you see in search results. It contains billions of facts about people, places, and things, allowing Google to provide more contextual and relevant search results. Similarly, Facebook uses a knowledge graph called the social graph to understand and represent the complex web of relationships between its users, their interests, and their activities on the platform. One of the most powerful features of knowledge graphs is their ability to enable complex query answering. Traditional databases often struggle with queries that require traversing multiple relationships or inferring new connections. Knowledge graphs, however, excel at this type of task. For instance, a knowledge graph could easily answer a query like, what actors have starred in movies directed by Christopher Nolan and also appeared in a James Bond film, by traversing the connections between actors, movies, and directors. Despite their power, knowledge graphs face significant scalability challenges, especially when dealing with massive amounts of data. As the number of nodes and edges grows, the computational resources required to maintain and query the graph increase exponentially. This is particularly challenging for companies dealing with internet-scale data. Techniques like distributed computing and graph partitioning are often employed to manage these large-scale knowledge graphs effectively. The integration of machine learning with knowledge graphs represents an exciting frontier in data science. Machine learning algorithms can be used to automatically extract information from unstructured data sources and add it to knowledge graphs, keeping them up to date with minimal human intervention. Conversely, knowledge graphs can enhance machine learning models by providing rich, structured background knowledge that can improve the accuracy and interpretability of predictions. Knowledge graphs are also playing a crucial role in advancing natural language processing. By providing a structured representation of world knowledge, they help language models better understand context and relationships between concepts. This has led to improvements in tasks like question answering, text summarization, and even language translation. In the financial sector, knowledge graphs are being used to detect fraud and assess risk. By representing complex financial transactions and relationships between entities, these graphs can reveal patterns that might indicate fraudulent activity or potential financial risks that traditional methods might miss. The healthcare industry is another area where knowledge graphs are making significant impacts. By integrating diverse medical data sources, from patient records and research papers to genetic information and drug interactions, knowledge graphs are helping to accelerate drug discovery, improve diagnosis accuracy, and enable more personalized treatment plans. While knowledge graphs excel at connecting data points, they still rely on a crucial element to truly unlock their potential. The missing piece that breathes life into these intricate webs of information is semantics, the key to decoding the true meaning behind our data. Semantics in the context of data science is the study of meaning in data. It goes beyond simple categorization or relationship mapping to understand the nuances and context of information. This field is essential because it bridges the gap between human language and machine interpretation, allowing computers to grasp the subtleties and complexities of human communication. The importance of context in semantic understanding cannot be overstated. Consider the word bank. Without context, it's impossible to determine whether we're referring to a financial institution or the edge of a river. Semantic analysis takes into account the surrounding words, the overall topic, and even cultural references to accurately interpret the intended meaning. Natural language processing, NLP, plays a crucial role in semantic analysis. NLP techniques allow machines to parse human language, breaking it down into components like parts of speech, entities, and relationships. Advanced NLP models can now understand context, idioms, and even detect sentiment, bringing us closer to true machine comprehension of human communication. Semantic networks are a powerful tool in this field, representing concepts as nodes and their relationships as edges. These networks bear a striking resemblance to knowledge graphs, but with a focus on meaning rather than just connections. For example, in a semantic network for animals, the concept dog might be linked to mammal is a relationship, bark, can-do relationship, and fur has a relationship. The application of semantics significantly improves search result relevance. Traditional keyword-based searches often fall short when dealing with synonyms, homonyms, or context-dependent terms. Semantic search engines, on the other hand, understand the user's intent and the context of their query. This leads to more accurate and helpful results, even when the exact search terms don't appear in the target content. However, semantic analysis faces several challenges, particularly in handling ambiguity. Human language is riddled with words and phrases that can have multiple meanings depending on context. Sarcasm, metaphors, and cultural references further complicate the task. Resolving these ambiguities requires sophisticated algorithms that can analyze broader context and sometimes even draw on external knowledge sources. The future of semantic web technologies looks promising. The vision of a semantic web where all online information is machine-readable and interlinked is gradually becoming a reality. This evolution will enable more intelligent and context-aware applications, from virtual assistants that truly understand our needs to automated systems that can interpret and act on complex instructions without human intervention. Semantic technologies are already making significant impacts across various industries. In healthcare, semantic analysis of medical records and research papers is improving diagnosis, accuracy, and treatment recommendations. In finance, it's enhancing fraud detection by understanding the context and implications of transactions. In e-commerce, it's powering recommendation engines that understand not just what customers bought, but why they bought it. The integration of semantics with other data science pillars like taxonomy, ontology, and knowledge graphs creates a powerful framework for understanding and utilizing data. While taxonomies provide structure and ontologies define relationships, semantics breathe life into these frameworks by infusing them with meaning and context. Consider a scenario where a company is analyzing customer feedback. A taxonomy might categorize comments into broad topics like product quality or customer service. An ontology could define relationships between these categories and specific products or services. But it's semantic analysis that can interpret the nuances of customer sentiment. Understanding that a phrase like, "this product is sick," could be highly positive in some contexts and negative in others. The impact of semantic understanding on data accuracy is substantial. By correctly interpreting the meaning and context of data, organizations can reduce errors and misinterpretations that often plague data-driven decision-making. Some studies suggest that implementing robust semantic analysis can improve data accuracy by up to 40%, a significant boost in an era where data quality can make or break business strategies. While each pillar of the TOKS framework offers unique strengths, their true potential emerges when they work in concert. How exactly do taxonomy, ontology, knowledge graphs, and semantics combine to revolutionize data analysis? Let's explore the synergy that occurs when these four pillars are integrated into a unified system. The integration process begins with taxonomy, which provides the foundational structure for organizing information. This hierarchical classification system serves as a blueprint for ontology development. As ontologies are created, they build upon the basic categories established by the taxonomy, adding layers of relationships and properties between entities. This expansion transforms a simple classification system into a rich network of interconnected concepts. Once a robust ontology is in place, it informs the structure of knowledge graphs. The classes, instances, and properties defined in the ontology become the nodes, edges, and attributes of the knowledge graph. This transformation allows for visual representation of complex relationships and enables powerful querying capabilities. The knowledge graph essentially brings the ontology to life, making it possible to traverse connections and uncover hidden patterns in the data. Semantics then steps in to enhance the interpretation of the knowledge graph data. By applying semantic analysis techniques, the system can understand the context and meaning behind the information represented in the graph. This semantic layer allows for more nuanced queries and more accurate interpretation of results. For example, it can help distinguish between different meanings of the same word based on context or understand the implications of certain relationships within the graph. To illustrate how these pillars work together in practice, consider a real-world example from the pharmaceutical industry. A drug discovery project might start by creating a taxonomy of chemical compounds, biological targets, and disease states. This taxonomy would then be expanded into an ontology, defining relationships such as compound interacts with target or target is associated with disease. This ontology would form the basis of a knowledge graph, visually representing the vast network of compounds, targets, and diseases. Semantic analysis would then be applied to interpret research papers, clinical trial data, and other relevant information, enriching the knowledge graph with contextual understanding. The integration of these four pillars allows researchers to ask complex questions that traverse multiple relationships. For instance, they could query, what compounds similar to drug X have shown efficacy against targets associated with disease Y, but have not yet been tested for disease Z? This type of multifaceted query, combining structural organization, relationship mapping, and semantic understanding, would be extremely difficult without an integrated TOKS system. The synergy between these pillars significantly improves data quality and analysis accuracy. By providing a clear structure, defining relationships, enabling visual representation, and ensuring accurate interpretation, the integrated system reduces errors and misunderstandings that can occur when working with complex data sets. This improvement in data handling can lead to more reliable insights and better informed decision-making. However, implementing a fully integrated TOKS system is not without its challenges. One major hurdle is the initial setup and maintenance of the system. Developing comprehensive taxonomies and ontologies requires significant time and expertise. Ensuring that these structures remain up to date as new information emerges can be a continuous effort. Another challenge lies in managing the scale and complexity of knowledge graphs as they grow. As more data is added, the computational resources required to query and analyze the graph increase. Balancing the depth of information with system performance becomes crucial. Semantic analysis also presents its own set of challenges, particularly when dealing with ambiguity in language or domain-specific terminology. Ensuring that the system correctly interprets the meaning and context of information across various sources and formats requires sophisticated natural language processing capabilities. Artificial intelligence and machine learning play a crucial role in addressing these challenges and enhancing TOKS integration. Machine learning algorithms can assist in automating the process of taxonomy and ontology development by analyzing large data sets and suggesting relevant categories and relationships. They can also help in maintaining and updating these structures over time. In the realm of knowledge graphs, AI can aid in automatically extracting information from unstructured data sources to populate and expand the graph. Machine learning techniques can also optimize graph traversal and querying, improving performance as the graph grows in size and complexity. For semantic analysis, advanced natural language processing models powered by machine learning can handle increasingly complex linguistic structures and contextual nuances. These models can be trained on domain-specific data to improve their accuracy in interpreting specialized terminology and concepts. The integration of AI and machine learning with TOKS systems creates a powerful feedback loop. As the AI systems interact with the structured data provided by the TOKS framework, they can uncover new patterns and relationships, which in turn can be used to refine and expand the existing taxonomies, ontologies, and knowledge graphs. As we've seen, TOKS systems can unlock incredible insights. But before we can build these powerful frameworks, we need to understand our starting point. Imagine trying to renovate a house without first inspecting the foundation. That's exactly what many companies do with their data, and the consequences can be catastrophic. The analysis phase is critical in any data transformation journey. It involves a comprehensive assessment of existing data structures, processes, and systems. This step is not just about identifying what data you have, but understanding how it's organized, how it flows through your organization, and how effectively it's being used. One of the primary tools in this phase is the data structure audit. This process involves systematically examining your data assets, including databases, data warehouses, and even unstructured data sources like documents and emails. The audit looks at several key components: data quality, data completeness, data consistency, and data accessibility. During these audits, it's common to uncover a host of issues in legacy data systems. These can range from data silos that prevent effective information sharing to inconsistent naming conventions that make data difficult to find and use. Outdated data models that no longer reflect current business needs are another frequent problem, as are redundant or conflicting data sets that create confusion and inefficiency. Analyzing large-scale data structures presents its own set of challenges. Fortunately, there are numerous tools and techniques available to help. Data profiling tools can automatically scan large data sets to identify patterns, anomalies, and potential quality issues. Visualization tools can help make sense of complex data relationships, while metadata management systems can provide a clear picture of data lineage and dependencies. When evaluating the effectiveness of your current data organization, consider the following checklist. 1. Is your data easily discoverable and accessible to those who need it? 2. Can your data be easily integrated across different systems and departments? 3. Does your data structure support efficient querying and analysis? 4. Is your data consistent and reliable across different sources? 5. Does your data model align with current business processes and needs? 6. Can your data structure accommodate new types of data as your business evolves? A crucial part of the analysis phase is identifying gaps in your current taxonomy and ontology implementations. This involves comparing your existing structures against industry standards and best practices. Are there important categories or relationships missing from your current model? Does your taxonomy provide the right level of granularity for your needs? Does your ontology capture all the relevant relationships between entities in your domain? While technical analysis is important, don't underestimate the value of stakeholder interviews in this phase. The people who work with your data daily often have invaluable insights into its strengths and weaknesses. They can highlight practical issues that might not be apparent from a purely technical analysis, such as usability problems or missing data elements that are crucial for specific business processes. Measuring the semantic richness of your existing data is another important aspect of the analysis phase. This involves assessing how well your current data structures capture and convey meaning. Are your data elements well-defined and unambiguous? Do your data models include relevant, contextual information? Can your systems handle complex queries that require understanding of context and relationships? One way to measure semantic richness is through the use of semantic differential scales. These tools can help quantify how well your data captures nuanced meanings and relationships. Another approach is to analyze query logs to see how often users need to reformulate their queries or combine multiple queries to get the information they need. A high rate of query reformulation often indicates a lack of semantic richness in the underlying data structure. The payoff for conducting a thorough analysis can be substantial. By identifying issues early and gaining a comprehensive understanding of your current data landscape, you can significantly reduce the costs and risks associated with data restructuring projects. In fact, studies have shown that a well-executed analysis phase can reduce overall data restructuring costs by up to 30%. This cost saving comes from several factors. First, by identifying and addressing issues early, you avoid the expensive process of reworking implementations later in the project. Second, a clear understanding of your current state allows for more accurate project scoping and resource allocation. Finally, by involving stakeholders early and understanding their needs, you increase the likelihood of creating a solution that truly meets business requirements, reducing the need for costly revisions down the line. 9. Design, crafting the ideal TOKS framework. Now that we've laid the groundwork with our analysis, it's time to architect the future of our data ecosystem. Designing an ideal TOKS framework isn't just about organizing information, it's about creating a living, breathing system of knowledge that can adapt and grow with our needs. So, how do we breathe life into our data structures? The key principles of designing a TOKS framework revolve around clarity, flexibility, and scalability. We need to create a system that's easy to understand and navigate, yet robust enough to handle complex relationships and large volumes of data. It's crucial to strike a balance between specificity and generality, ensuring our framework can accommodate both current and future needs. When creating a domain-specific taxonomy, we start by identifying the core concepts and categories relevant to our field. This process involves extensive collaboration with subject matter experts and stakeholders to ensure we're capturing the full scope of the domain. We begin with broad categories and progressively refine them into more specific subcategories. For example, in a retail context, we might start with top-level categories like products, customers, and transactions, then break these down further based on specific attributes and relationships. As we extend our taxonomy into a comprehensive ontology, we focus on defining the relationships between entities and their properties. This step transforms our hierarchical structure into a rich network of interconnected concepts. We identify key relationships such as is a, part of, and related to, and define properties that describe the attributes of each entity. In our retail example, we might define relationships like customer purchases product or properties like product has price. Knowledge graph schema design builds upon our ontology, translating conceptual relationships into a formal structure that can be queried and analyzed. Best practices in this area include defining clear entity types, establishing consistent naming conventions, and carefully considering the directionality and cardinality of relationships. It's also important to design for performance, considering how the graph will be traversed and queried in real-world scenarios. Several tools and technologies can aid in TOKS framework design. Ontology editors like Protégé provide intuitive interfaces for creating and managing ontologies. Graph databases such as Neo4j offer powerful platforms for implementing and querying knowledge graphs. For semantic analysis, natural language processing libraries like spaCy or NLTK can be invaluable. It's crucial to choose tools that integrate well with existing systems and support industry standards. Incorporating semantic layers into our design involves more than just adding metadata. We need to consider how our system will interpret and use the meaning encoded in our data. This might involve implementing controlled vocabularies, developing domain-specific thesauri, or integrating with existing semantic resources like WordNet. The goal is to create a system that can understand and reason about the content it contains, not just store and retrieve it. Scalability and flexibility are paramount in the design phase. Our TOKS framework needs to handle growing volumes of data and evolving business needs. This might involve designing for distributed processing, implementing modular architectures that can be easily extended, or planning for regular updates to our taxonomy and ontology. We should also consider how our framework will integrate with other systems and data sources, both now and in the future. Designing for future AI and machine learning integration is increasingly important. This might involve structuring our data in ways that are conducive to machine learning algorithms, such as ensuring consistent feature representation. We should also consider how our knowledge graph can serve as a foundation for AI reasoning, potentially incorporating probabilistic elements or support for uncertainty. A well-designed TOKS framework can significantly streamline data integration processes. By providing a clear structure for data organization and relationships, we can automate many aspects of data mapping and transformation. This can lead to substantial time savings in data integration projects, potentially reducing integration time by up to 40%. This efficiency gain comes from reduced manual effort in data mapping, fewer errors in data interpretation, and faster query processing due to optimized data structures. Let's shift gears from theory to practice and explore how we can transform our TOKS vision into a tangible working system that revolutionizes our data processes. Building a robust TOKS infrastructure is a complex but rewarding endeavor that requires careful planning and execution. The first step in developing a TOKS infrastructure is implementing taxonomies in database systems. This involves creating a hierarchical structure within your database that reflects the categorization scheme you've designed. Many modern database management systems offer built-in support for hierarchical data structures, such as Oracle's hierarchical queries or PostgreSQL's LTRE module. These tools allow you to efficiently store and query hierarchical data, making it easier to navigate and analyze your taxonomy. When it comes to encoding ontologies in machine-readable formats, there are several established standards to choose from. The Web Ontology Language, OWL, is a popular choice, offering a rich set of constructs for expressing complex relationships and constraints. Another option is the Resource Description Framework, RDF, which provides a flexible graph-based data model. These formats allow you to represent your ontology in a way that machines can interpret and reason about, enabling automated inference and knowledge discovery. Building and maintaining knowledge graphs requires specialized tools and platforms. Graph databases like Neo4j, Amazon Neptune, or TigerGraph are designed specifically for storing and querying graph-structured data. These platforms offer high-performance query engines that can traverse complex relationships quickly, making them ideal for implementing knowledge graphs at scale. Additionally, visualization tools like Gephi or Cytoscape can help you explore and analyze your knowledge graph, providing valuable insights into the structure and patterns within your data. Integrating semantic analysis capabilities into your TOKS infrastructure involves implementing natural language processing (NLP) techniques. Libraries such as Spacy, NLTK, or Stanford Core NLP provide pre-trained models and tools for tasks like named entity recognition, part-of-speech tagging, and dependency parsing. These capabilities allow your system to extract meaning from unstructured text, enriching your knowledge graph with information from diverse sources. Developing APIs for accessing TOKS components is crucial for making your infrastructure accessible and usable across your organization. RESTful APIs are a common choice, offering a standardized way to interact with your TOKS system over HTTP. GraphQL is another option that provides more flexibility in querying complex data structures. When designing your APIs, consider factors like authentication, rate limiting, and versioning to ensure security and maintainability. As you build your TOKS infrastructure, you'll likely encounter several common challenges. One major hurdle is data quality and consistency. Inconsistent or erroneous data can undermine the effectiveness of your taxonomy, ontology, and knowledge graph. Implementing robust data validation and cleansing processes is essential to maintain the integrity of your TOKS system. Another challenge is scalability, particularly as your knowledge graph grows. Employing techniques like distributed computing and graph partitioning can help manage large-scale knowledge graphs effectively. Data governance plays a crucial role in the development process of a TOKS infrastructure. Establishing clear policies and procedures for data management ensures that your TOKS components remain accurate, up-to-date, and compliant with relevant regulations. This includes defining roles and responsibilities for data stewardship, implementing change management processes, and ensuring proper documentation of your TOKS components. One often overlooked aspect of TOKS development is the importance of user adoption and training. Even the most sophisticated TOKS infrastructure will fall short if users don't understand how to leverage it effectively. Developing comprehensive training programs and user-friendly interfaces can significantly improve adoption rates and maximize the value of your TOKS investment. As you progress through the development phase, it's important to implement a robust testing and quality assurance process. This should include unit testing of individual components, integration testing to ensure different parts of the system work together seamlessly, and performance testing to identify and address bottlenecks. Automated testing tools can help streamline this process and catch issues early in the development cycle. Another consideration in TOKS development is the integration with existing systems and workflows. Your TOKS infrastructure shouldn't exist in isolation, but should seamlessly connect with other data sources, analytics platforms, and business applications. This might involve developing custom connectors or leveraging Enterprise Service Bus (ESB) technologies to facilitate data flow between systems. Now that we've laid the groundwork for our TOKS infrastructure, it's time to tackle the most crucial phase, implementation. This is where theory meets practice, and the true value of our carefully designed system is put to the test. Let's explore how organizations can effectively deploy TOKS in real-world scenarios and unlock its full potential. The first step in implementing TOKS is developing a comprehensive rollout strategy. This plan should outline the phases of implementation, starting with a pilot project in a specific department or data domain. By beginning with a smaller scope, organizations can identify and address any unforeseen challenges before scaling up. The strategy should also include clear timelines, resource allocation, and key performance indicators to measure success. Data migration is a critical component of TOKS implementation. This process involves mapping existing data structures to the new TOKS-compliant framework. It's essential to approach this task methodically, ensuring that data integrity is maintained throughout the transition. Organizations often employ specialized data migration tools and conduct thorough testing to verify the accuracy of the transferred data. This phase may also involve data cleansing and normalization to align with the new taxonomies and ontologies. Change management is paramount when introducing a new system like TOKS. Employees may be resistant to altering their established workflows or learning new tools. To combat this, organizations should focus on clear communication about the benefits of TOKS, both for individual roles and the company as a whole. Providing comprehensive training programs and support resources can help ease the transition. It's also beneficial to identify and nurture TOKS champions within different departments who can advocate for the system and assist their colleagues. Several industries have successfully implemented TOKS systems, yielding impressive results. In healthcare, a large hospital network used TOKS to create a unified view of patient data across multiple facilities. This implementation improved diagnostic accuracy and reduced redundant tests, leading to better patient outcomes and cost savings. In the financial sector, a global bank leveraged TOKS to enhance its fraud detection capabilities, resulting in a 30% increase in the identification of suspicious transactions. Training staff on TOKS-enhanced data systems is crucial for maximizing adoption and utilization. This training should be role-specific, focusing on how TOKS can improve each employee's day-to-day tasks. Hands-on workshops, video tutorials, and interactive e-learning modules can cater to different learning styles. Additionally, creating a centralized knowledge base where employees can find answers to common questions can significantly reduce the burden on IT support teams. While TOKS offers numerous benefits, implementation is not without its challenges. One common pitfall is underestimating the time and resources required for a successful rollout. Organizations should be prepared for a potentially lengthy process and avoid rushing to meet arbitrary deadlines. Another issue is failing to secure buy-in from key stakeholders across different departments. To mitigate this, involve representatives from various teams in the planning and decision-making processes from the outset. Continuous monitoring and optimization are essential for maintaining the effectiveness of a TOKS system. Regular audits should be conducted to ensure that taxonomies and ontologies remain relevant and accurate as business needs evolve. Performance metrics should be tracked to identify areas for improvement, such as query response times or data retrieval accuracy. User feedback should be actively solicited and incorporated into system updates. You've implemented TOKS, but how do you know if it's truly making a difference? Let's dive into the world of data-driven evaluation, where we'll uncover methods to quantify the impact of your TOKS investment and guide its evolution. Key performance indicators, KPIs, are essential for measuring TOKS effectiveness. These metrics should align with your organization's specific goals and can include data retrieval speed, query accuracy, and user satisfaction. For example, you might track the average time it takes users to find relevant information before and after TOKS implementation. A reduction in search time could indicate improved data organization and accessibility. To measure improvements in data retrieval and analysis, consider implementing A/B testing. This involves comparing the performance of TOKS-enhanced systems against traditional ones. You could set up two parallel environments, one using the new TOKS framework and another using the old system. Then measure metrics like query response times, the number of relevant results returned, and the accuracy of data analysis outcomes. This direct comparison can provide concrete evidence of TOKS benefits. Evaluating the accuracy of knowledge graph queries requires a multifaceted approach. One method is to use a set of predefined benchmark queries with known correct answers. Run these queries through your knowledge graph and compare the results to the expected outcomes. Additionally, you can employ domain experts to review a sample of query results and assess their accuracy and relevance. This human evaluation can catch nuances that automated tests might miss. Assessing semantic understanding in data systems is crucial for ensuring that your TOKS implementation correctly interprets and processes information. Natural language processing tools can be used to evaluate how well your system understands context and meaning. For instance, you could test the system's ability to correctly classify documents, extract entities, or answer complex questions that require reasoning across multiple data points. User feedback is invaluable for evaluating TOKS implementations. Develop surveys and conduct interviews with end users to gather qualitative data on their experience with the new system. Ask about ease of use, perceived improvements in data accessibility, and any challenges they've encountered. This feedback can highlight areas for improvement and validate the system's effectiveness from a user perspective. A/B testing can be extended beyond basic performance metrics to assess the broader impact of TOKS on business processes. For example, you could compare the time it takes data scientists to develop and deploy machine learning models using TOKS-enhanced data versus traditional data structures. Measure factors like model accuracy, development time, and the ability to incorporate diverse data sources. This can demonstrate how TOKS contributes to more efficient and effective data science workflows. Long-term return on investment (ROI) analysis is crucial for justifying and optimizing TOKS investments. Track costs associated with TOKS implementation, including software, hardware, training, and ongoing maintenance. Compare these against measurable benefits, such as increased productivity, reduced data management costs, and new revenue opportunities enabled by improved data insights. Consider both tangible and intangible benefits, such as improved decision-making capabilities and enhanced data governance. To use evaluation results for continuous improvement, establish a feedback loop within your organization. Regularly review KPIs, user feedback, and ROI metrics to identify areas for enhancement. This could involve refining taxonomies, expanding ontologies, or optimizing knowledge graph structures. By treating TOKS as an evolving system rather than a one-time implementation, you can ensure it continues to meet changing business needs and technological advancements. One powerful technique for ongoing evaluation is to implement automated monitoring of TOKS performance. Set up dashboards that track key metrics in real time, allowing you to quickly identify and address any issues. This could include monitoring query response times, system uptime, and the growth of your knowledge graph. Automated alerts can notify administrators when performance falls below certain thresholds, enabling proactive maintenance and optimization. Consider the impact of TOKS on data quality and consistency across your organization. Measure improvements in data standardization, reduction in duplicate records, and increased data completeness. These factors can have a significant impact on the overall reliability and usefulness of your data assets. Evaluate how TOKS enhances cross-departmental collaboration and knowledge sharing. Track metrics such as the number of interdepartmental data requests, the time taken to fulfill these requests, and the frequency of data-driven collaborations. Improvements in these areas can indicate that TOKS is breaking down data silos and fostering a more integrated approach to data management. Assess the impact of TOKS on regulatory compliance and risk management. Measure how quickly and accurately your organization can respond to audit requests or regulatory changes. A well-implemented TOKS system should improve your ability to track data lineage, manage access controls, and ensure data privacy, all of which are crucial for maintaining compliance in today's regulatory environment. Finally, don't overlook the potential of TOKS to drive innovation within your organization. Evaluate how the improved data accessibility and understanding provided by TOKS contributes to new product development, process improvements, or market insights. This could involve tracking the number of new data-driven initiatives, the time to market for data-dependent products, or the generation of novel insights that lead to competitive advantages. While TOKS drives innovation across organizations, its impact on artificial intelligence is even more profound. The structured knowledge and semantic understanding provided by TOKS are revolutionizing how AI systems learn, reason, and interact with the world. This integration is pushing the boundaries of what's possible in machine learning and bringing us closer to truly intelligent machines. Knowledge graphs, a key component of TOKS, are transforming machine learning model performance. By providing a rich, interconnected structure of information, knowledge graphs allow AI systems to leverage pre-existing knowledge and relationships. This contextual understanding enables models to make more accurate predictions and inferences, even with limited training data. For example, a machine learning model tasked with identifying objects in images can use a knowledge graph to understand relationships between objects, their properties, and typical contexts. This additional layer of information can significantly improve classification accuracy and reduce errors. Semantic understanding, another pillar of TOKS, is enhancing natural language processing (NLP) capabilities. Traditional NLP models often struggle with ambiguity and context in human language. By incorporating semantic networks and ontologies, TOKS-enhanced NLP systems can better interpret the nuances of language, understand context, and even grasp subtle cultural references. This improved comprehension leads to more accurate language translation, more natural human-computer interactions, and more sophisticated text analysis capabilities. TOKS is also playing a crucial role in the development of explainable AI systems. As AI becomes more prevalent in decision-making processes, there's a growing need for transparency and interpretability. TOKS provides a framework for AI systems to explain their reasoning in human understandable terms. By mapping AI decisions to concepts and relationships defined in ontologies and knowledge graphs, these systems can provide clear explanations for their outputs. This explainability is particularly valuable in critical domains like healthcare and finance, where understanding the rationale behind AI recommendations is essential. Across industries, TOKS-powered AI applications are demonstrating remarkable capabilities. In healthcare, AI systems enhanced with medical ontologies and knowledge graphs are improving diagnostic accuracy and treatment recommendations. These systems can integrate diverse data sources, understand complex medical relationships, and provide insights that consider a patient's entire medical history and relevant research findings. In the financial sector, TOKS-enhanced AI is revolutionizing fraud detection and risk assessment. By understanding the intricate relationships between financial entities and transactions, these systems can identify suspicious patterns that might elude traditional rule-based approaches. One of the most promising applications of TOKS in AI is its potential to reduce bias in decision-making processes. AI systems can inadvertently perpetuate or amplify biases present in their training data. TOKS can help mitigate this issue by providing a more comprehensive and balanced knowledge base. By incorporating diverse perspectives and explicitly defining relationships between concepts, TOKS can help AI systems make more fair and equitable decisions. For instance, in hiring processes, a TOKS-enhanced AI system could be designed to consider a wide range of qualifications and experiences, reducing the risk of discrimination based on limited criteria. In the realm of recommendation systems, TOKS is enabling more sophisticated and personalized suggestions. Traditional recommendation algorithms often rely on simple similarity metrics or collaborative filtering. TOKS-enhanced systems can leverage rich knowledge graphs to understand the deeper connections between items and user preferences. For example, a music recommendation system could use a comprehensive music ontology to understand not just genre similarities, but also the historical and cultural contexts of different music styles. This deeper understanding allows for more nuanced and diverse recommendations, improving user satisfaction and discovery of new content. Looking to the future, TOKS holds immense potential in the development of cognitive computing and artificial general intelligence, AGI. As we strive to create AI systems that can reason and learn across diverse domains like humans, the structured knowledge and semantic understanding provided by TOKS become increasingly crucial. TOKS can provide the foundational knowledge and reasoning frameworks that AGI systems would need to understand and interact with the world in a truly intelligent manner. While AGI remains a distant goal, TOKS is already pushing the boundaries of what's possible in narrow AI applications. Perhaps most importantly, the integration of TOKS with AI and machine learning can lead to significant improvements in model accuracy. Early studies and implementations have shown that TOKS-enhanced AI systems can achieve up to a 30% increase in accuracy across various tasks. This improvement is not just a marginal gain, it represents a substantial leap in AI capabilities that can translate to more reliable and effective AI applications across industries. The implementation of taxonomy, ontology, knowledge graph, and semantics TOKS frameworks promises remarkable benefits for organizations, but the journey is rarely smooth sailing. While we've explored the potential of TOKS, it's crucial to acknowledge the hurdles that can derail even the most well-intentioned initiatives. Understanding these challenges is the first step towards overcoming them and realizing the full potential of TOKS in data science. One of the most pervasive challenges organizations face is maintaining up-to-date taxonomies and ontologies. As businesses evolve and new data types emerge, these structures can quickly become outdated. For instance, a retail company might find its product taxonomy struggling to accommodate the rapid influx of smart home devices or emerging sustainable product categories. Keeping these frameworks current requires ongoing effort and resources, often necessitating dedicated teams or roles focused on taxonomy and ontology management. Scalability issues in large-scale knowledge graph implementations present another significant hurdle. As organizations accumulate vast amounts of data, their knowledge graphs can grow to billions of nodes and edges. This exponential growth can strain computational resources, leading to slower query times and increased maintenance costs. Organizations may find themselves grappling with performance bottlenecks, especially when trying to perform complex traversals or analytics on these massive graphs. Ensuring data quality in semantic systems is a challenge that can make or break TOKS implementations. Semantic analysis relies heavily on the accuracy and consistency of the underlying data. Inconsistencies, errors, or ambiguities in the data can lead to misinterpretations and flawed insights. For example, a healthcare organization implementing TOKS might struggle with variations in medical terminology across different departments or institutions, potentially leading to critical misunderstandings in patient care. Resistance to TOKS adoption is a common organizational challenge that shouldn't be underestimated. Employees accustomed to traditional data management systems may view TOKS as unnecessarily complex or disruptive to their established workflows. This resistance can manifest as low engagement with new tools, reluctance to update existing processes, or even active pushback against the implementation. Overcoming this challenge requires a multifaceted approach, including clear communication of TOKS benefits, comprehensive training programs, and visible support from leadership. Handling ambiguity in semantic interpretation remains a persistent challenge in TOKS implementations. Natural language is inherently ambiguous, with words and phrases often having multiple meanings depending on context. For instance, in a financial services context, the term bank could refer to a financial institution, the act of depositing money, or even the side of a river. Developing systems that can accurately disambiguate these terms requires sophisticated natural language processing techniques and often domain-specific knowledge bases. Balancing complexity with usability in TOKS systems is a delicate act. While the power of TOKS lies in its ability to represent complex relationships and nuanced meanings, this complexity can overwhelm users if not managed carefully. Organizations must strike a balance between the depth of their taxonomies and ontologies and the ease with which users can navigate and utilize these structures. An overly complex system might offer theoretical advantages, but could lead to practical difficulties in adoption and day-to-day use. Ethical considerations in knowledge representation and AI integration are becoming increasingly important as TOKS systems grow more sophisticated. These systems have the potential to encode biases present in the data or in the minds of their creators. For example, a TOKS-enhanced AI system in human resources might inadvertently perpetuate gender or racial biases in hiring decisions if the underlying knowledge representations are not carefully scrutinized for fairness and inclusivity. Organizations must be vigilant in addressing these ethical concerns, implementing safeguards, and regularly auditing their systems for unintended biases. Despite these challenges, addressing them head-on can lead to significantly smoother TOKS implementations. Organizations that proactively tackle these issues often find that their TOKS initiatives proceed more efficiently and deliver greater value. By anticipating and planning for these common pitfalls, companies can potentially achieve up to 40% smoother implementations, reducing delays, cost overruns, and user frustration. Strategies for overcoming these challenges are diverse and multifaceted. To maintain up-to-date taxonomies and ontologies, organizations can implement automated monitoring systems that flag potential areas for update based on new data patterns or user feedback. Regular review cycles involving domain experts can ensure that these structures remain relevant and accurate. For scalability issues, organizations are increasingly turning to distributed computing solutions and advanced graph partitioning techniques. These approaches allow for more efficient processing of large-scale knowledge graphs, maintaining performance even as the graph grows. Some organizations are also exploring cloud-based solutions that offer scalable infrastructure on demand. Ensuring data quality in semantic systems often involves implementing rigorous data governance practices. This includes establishing clear data quality standards, implementing automated data validation processes, and fostering a culture of data stewardship across the organization. Some companies are leveraging machine learning techniques to assist in data cleansing and standardization, helping to maintain consistency in large and complex datasets. To overcome resistance to TOKS adoption, successful organizations often employ change management strategies that focus on demonstrating tangible benefits to end users. This might involve creating pilot programs that showcase TOKS capabilities in solving real business problems, or developing intuitive user interfaces that simplify interaction with complex TOKS systems. Personalized training programs that address the specific needs and concerns of different user groups can also be highly effective. Addressing ambiguity in semantic interpretation often requires a combination of advanced natural language processing techniques and domain-specific knowledge bases. Some organizations are developing hybrid systems that combine rule-based approaches with machine learning models to improve disambiguation accuracy. Continuous feedback loops that incorporate human expertise to refine these systems over time have shown promising results. Balancing complexity with usability often involves designing layered systems that allow users to interact with TOKS at different levels of complexity based on their needs and expertise. Intuitive visualization tools can help users navigate complex knowledge structures more easily, while APIs and query languages can provide power users with the ability to leverage the full complexity of the system when needed. As we stand on the cusp of a new era in data science, the future of taxonomy, ontology, knowledge graph, and semantics, TOKS frameworks, holds immense promise. The emerging trends in this field suggest we're on the verge of a data revolution that will redefine the limits of what's possible. Let's explore some of the most exciting developments on the horizon. One of the most promising trends is the development of federated knowledge graphs for global data integration. This approach aims to create a network of interconnected knowledge graphs that can seamlessly share and integrate information across different organizations, industries, and even countries. Imagine a world where medical researchers can instantly access and analyze data from hospitals worldwide, or where climate scientists can effortlessly combine data from various environmental agencies. Federated knowledge graphs could make this a reality, breaking down data silos and fostering unprecedented collaboration. The role of TOKS in advancing question-answering systems is another area of significant potential. As natural language processing techniques continue to improve, we can expect to see more sophisticated systems that can understand and respond to complex queries with human-like comprehension. These systems will not only provide more accurate answers, but also offer explanations and context, drawing on the rich relationships encoded in knowledge graphs and ontologies. An intriguing development is the integration of TOKS with blockchain technology for enhanced data provenance. This combination could revolutionize how we track and verify the origin, ownership, and modification history of data. In industries where data integrity is crucial, such as healthcare or finance, this could provide an immutable record of data lineage, ensuring transparency and trust in data-driven decision-making processes. The concept of self-evolving ontologies is particularly exciting. Traditional ontologies require manual updates to keep pace with changing knowledge domains. However, researchers are exploring ways to create ontologies that can automatically adapt and expand based on new information. These self-evolving ontologies could leverage machine learning algorithms to identify new concepts, relationships, and properties, ensuring that knowledge representations remain current and comprehensive without constant human intervention. TOKS frameworks are also set to play a pivotal role in enhancing virtual and augmented reality experiences. By providing rich, contextual information about objects and environments, TOKS can make virtual worlds more detailed and interactive. For example, in an educational VR experience about ancient civilizations, a TOKS-powered system could offer in-depth information about artifacts, historical figures, and cultural practices, creating a more immersive and informative experience. The potential of TOKS in developing more sophisticated digital twins is another area of innovation. Digital twins are virtual replicas of physical objects or systems used for simulation and analysis. By incorporating TOKS frameworks, these digital twins could become more accurate and dynamic, capable of representing complex relationships and behaviors. This could have far-reaching implications in industries like manufacturing, where digital twins could predict maintenance needs with unprecedented accuracy, or in urban planning, where city-scale digital twins could model the intricate interactions between infrastructure, population, and environment. Perhaps the most ambitious application of TOKS lies in its potential to enable true artificial general intelligence, as AGI. While current AI systems excel at specific tasks, AGI aims to create machines with human-like general intelligence. TOKS could provide the foundational knowledge structure and reasoning capabilities necessary for AGI. By combining vast knowledge graphs with advanced semantic understanding and inference capabilities, we might be able to create AI systems that can reason across domains, understand context, and even exhibit common sense, key components of general intelligence. The impact of these future TOKS innovations on data utilization across industries could be revolutionary. In healthcare, we might see personalized treatment plans that take into account not just a patient's medical history, but also environmental factors, genetic predispositions, and lifestyle choices, all seamlessly integrated through TOKS frameworks. In finance, TOKS could enable real-time risk assessment models that consider global economic trends, geopolitical events, and individual company performance, providing unprecedented insights for investors. In the realm of scientific research, TOKS innovations could accelerate discovery by enabling researchers to quickly identify connections between seemingly unrelated fields. For instance, a breakthrough in materials science could be rapidly applied to medical device development thanks to the ability of advanced TOKS systems to recognize relevant patterns and relationships across diverse domains. While the potential of TOKS is vast, many organizations struggle with where to begin. What if you could implement a TOKS framework in your company within the next year, transforming your data infrastructure and unlocking new insights? Let's explore a practical roadmap to make this a reality. The first step in implementing TOKS is conducting a comprehensive data structure audit. This involves systematically examining your existing data assets, including databases, data warehouses, and unstructured data sources. Use data profiling tools to automatically scan large data sets, identifying patterns, anomalies, and potential quality issues. Visualization tools can help make sense of complex data relationships, while metadata management systems provide a clear picture of data lineage and dependencies. During the audit, pay close attention to common issues in legacy data systems such as data silos, inconsistent naming conventions, outdated data models, and redundant or conflicting data sets. Evaluate your current data organization using a checklist that covers data discoverability, integration, querying efficiency, consistency, alignment with business processes, and accommodation of new data types. With a clear understanding of your current data landscape, the next step is building a compelling business case for TOKS investment. Highlight how TOKS can address the issues identified in your audit and quantify the potential benefits. For example, emphasize that a well-designed TOKS framework can reduce data integration time by up to 40% and improve data accuracy by up to 40%. Illustrate how TOKS can enhance various business functions, from improving customer recommendations in e-commerce to accelerating drug discovery in healthcare. When it comes to tools and platforms for TOKS implementation, there are numerous options available. For ontology development, consider using ontology editors like Protégé, which provide intuitive interfaces for creating and managing ontologies. Graph databases such as Neo4j, Amazon Neptune, or TigerGraph are excellent choices for implementing and querying knowledge graphs. For semantic analysis, leverage natural language processing libraries like Spacy or NLTK. A phased TOKS rollout is crucial for successful implementation. Start with a 6 to 12-month timeline, beginning with a pilot project in a specific department or data domain. This allows you to test and refine your approach before scaling up. In the first month, focus on planning and team assembly. Months 2 to 3 should be dedicated to the initial implementation of taxonomies and basic ontologies. In months 4 to 6, develop and integrate your knowledge graph. Use the remaining months to implement semantic analysis capabilities and refine the entire system based on feedback and performance metrics. For your pilot project, choose a well-defined area of your business where TOKS can deliver quick, visible benefits. This could be improving product categorization in an e-commerce platform or enhancing data integration in a specific research department. Keep the scope manageable and set clear, measurable objectives. Assembling the right team is critical for TOKS success. Key roles include data architects to design the overall TOKS framework, ontology engineers to develop and maintain ontologies, knowledge graph specialists to implement and optimize graph databases, and semantic analysts to ensure accurate interpretation of data. Additionally, you'll need data scientists to leverage the TOKS framework for advanced analytics and machine learning applications. To support your team's growth and keep up with evolving TOKS technologies, invest in continuous learning and professional development. Encourage team members to participate in online courses, attend conferences, and engage with TOKS communities. Platforms like Coursera and EDX offer specialized courses in ontology, engineering, and knowledge graph development. Professional associations such as the Semantic Web Science Association, SWSA, provide valuable resources and networking opportunities. By following this structured approach, organizations can successfully adopt TOKS within 6 to 12 months, laying the foundation for more sophisticated data management and analytics capabilities. Remember, the key to success lies in starting small, demonstrating value quickly, and gradually expanding the scope of your TOKS implementation. The world of taxonomy, ontology, knowledge graph, and semantics, TOKS, is in a constant state of flux. As technologies evolve and new applications emerge, professionals in this field must commit to ongoing education to stay relevant and effective. Continuous learning isn't just a nice to have, it's a necessity for those who want to remain at the forefront of TOKS implementation and innovation. To maintain a competitive edge, TOKS practitioners should focus on several key areas. First and foremost is keeping abreast of advancements in artificial intelligence and machine learning, as these technologies are increasingly integrated with TOKS frameworks. Understanding how AI algorithms can enhance ontology development, knowledge graph construction, and semantic analysis is crucial. Additionally, staying updated on new data modeling techniques, graph database technologies, and natural language processing methods is essential for pushing the boundaries of what's possible with TOKS. Fortunately, there are numerous resources available for those committed to continuous learning in TOKS. Online platforms like Coursera, edX, and Udacity offer specialized courses in ontology engineering, knowledge graph development, and semantic web technologies. These courses often provide hands-on experience with cutting-edge tools and methodologies. Academic journals, such as the Journal of Web Semantics and the Semantic Web Journal, publish the latest research and innovations in the field. Following these publications can provide insights into emerging trends and theoretical advancements. Professional communities and forums play a vital role in TOKS learning. Organizations like the Semantic Web Science Association, SWSA, host conferences, workshops, and webinars that bring together experts from around the world. These events offer opportunities to learn about real-world applications of TOKS, discuss challenges with peers, and discover new tools and techniques. Online forums and social media groups dedicated to TOKS topics provide platforms for asking questions, sharing experiences, and collaborating on projects. Applying new TOKS concepts in practical scenarios is crucial for solidifying knowledge and driving innovation. One effective strategy is to create small-scale projects that implement recently learned techniques. For example, after learning about a new ontology design pattern, you could apply it to a subset of your organization's data and evaluate its effectiveness. Another approach is to participate in open-source TOKS projects, which allows you to contribute to real-world applications while learning from experienced developers. Setting up a personal learning plan is key to achieving mastery in TOKS. Start by assessing your current knowledge and identifying gaps. Then set specific, measurable goals for what you want to learn over the next 3, 6, and 12 months. Break these goals down into smaller, actionable steps, such as completing a certain number of courses, reading a set number of research papers, or implementing specific TOKS concepts in your work. Regularly review and adjust your plan based on your progress and changing industry trends. The interdisciplinary nature of TOKS means that cross-disciplinary knowledge can significantly enhance your expertise. Understanding related fields such as data science, information architecture, and cognitive computing can provide valuable insights and spark innovative ideas. For instance, knowledge of cognitive science can inform the design of more intuitive and user-friendly ontologies. Similarly, familiarity with graph theory can lead to more efficient knowledge graph algorithms. As organizations increasingly recognize the value of TOKS, career opportunities in this field are expanding. Specializing in TOKS can open doors to roles such as ontology engineer, knowledge graph specialist, or semantic data architect. These positions often come with the responsibility of shaping an organization's data strategy and driving digital transformation initiatives. Moreover, TOKS expertise is increasingly sought after in fields like healthcare, finance, and e-commerce, where sophisticated data integration and analysis are critical. The payoff for continuous learning in TOKS can be substantial. Professionals who consistently update their skills and knowledge often see their capabilities improve by up to 20% year over year. This improvement translates to more efficient TOKS implementations, more accurate data analysis, and the ability to tackle increasingly complex data challenges. Moreover, staying at the cutting edge of TOKS can lead to innovations that give organizations a significant competitive advantage in their respective industries. As we wrap up our exploration of taxonomy, ontology, knowledge graphs, and semantics, TOKS, it's clear that this framework has the power to revolutionize how we handle and interpret data. By combining these 4 pillars, organizations can create a robust foundation for advanced analytics, machine learning, and artificial intelligence applications. The true strength of TOKS lies in its integrated approach. While each component offers unique benefits, their synergy creates a comprehensive system that enhances data accuracy, improves retrieval speed, and enables more sophisticated analysis. This holistic approach can lead to significant improvements across various industries from healthcare to finance. For those eager to embark on their TOKS journey, remember that implementation doesn't have to be overwhelming. Start with small, practical steps in a specific domain or department. As you gain experience and witness the benefits firsthand, you can gradually expand your TOKS framework across your organization. The path to mastering TOKS may be challenging, but the potential rewards in terms of data-driven insights and innovation are well worth the effort.